1 out of 40. Sweet. Wrong course. There we go. Stack operation. Sweet stacks. Life is getting tired, man. And I apologize for the energy level. Like the time change every year just wrecks me, and not in a good way. Like I'll be fine in a day or so, but those first few days are just so brutal. And you guys actually have stuff to do. I just sit around. Alrighty. So here's where we're at. And I'm going to stop at the same spot we stopped in A1. So I don't know how long this will go. We went the full time and didn't get through all the slides. So we'll stop at some point and then pick it up again on Tuesday. Don't forget there's no class on Thursday. No class on Thursday. I could turn this on, huh? Oda. That's not terrible. Yeah, so Thursday you guys should take off. Literally just take off. Don't do anything on Thursday. I'm not working on Thursday. It's spring break. All righty, so on Thursday of last week, we were down here in the heap, right? So we're talking heap stuff, using malloc and free and so on, and how the heap is constructed. And we looked at different ways to manage the space in the heap in terms of managing the free blocks, coalescing them into larger chunks when we're doing freeze, and we end up all these holes all over the heap, which is called fragmentation. There were two kinds of fragmentation, as I recall, internal and external. So that was all last week. This week, we're starting in on the other big structure in the process, which is this user stack up here. So the stack, I mean, it does a couple of things for us. Let's look at just really quickly to refresh your memory of what a stack does. I won't spend a lot of time because you should have seen stacks before, at least in one other course, maybe 2 or 3. So generically, a stack is essentially a LIFO queue, last in, first out. All the operations in a stack are done at the head. So we don't have to, like in your linked list, I was asking you to walk all the way down the linked list to find the bottom, do operations at the bottom essentially. In a stack, everything happens at the top. And plate at the dining hall, you put a plate on that stack, it's got springs underneath. The stack shrinks down a little bit when you put a plate on top. When you take a plate off, that stack comes up a little bit, so you see the one that was below that. So the 3 operations on stacks, push will push a value onto the stack, onto the top of the stack. Pop will pop that value off of the top of the stack. And then peek allows us to look at the top without changing anything. So you just take a quick peek, see what's up there. Basically, like here, if I've got a head pointer to the top of the stack, I'll start it out as null. And if I'm implementing this as a linked list, like as probably we will, like these are all just structs, but I'm going to push something onto the stack. I'm going to push a 5. So head's null here. Push 5 just means that 5 is now the top of that stack. That's where head points. If I push a 42, now I've got 42 on the top of the stack right here, and 5 is below that. And then a pop will pop the top of the stack off. So if I do a pop, that 42 comes off, and now head's going to point to the 5 that was below it. If I pop the 5 off, now the stack is empty. I can tell the stack is empty if head is null. Like that's just basic stack operation. There's nothing fancy there. It's actually much easier than doing the linked list stuff that you guys did, although you can probably leverage your linked list code, at least some of it, and just modify it slightly to work as a stack instead of a singly linked list. I think you'll be fine with those. So that's a stack, like a generic stack. The runtime stack, this piece up here, that user stack, that's going to get created as the program is loading. So I said on Thursday that there's a function called exec that is part of the kernel. And exec is called as I'm starting to load the program in. Exec is what copies things like the structure of the parent process. So the parent process is probably going to be the root process. It's going to copy the structure of that over into the new process and then start to fill in the values. It's like the .text portion will have the code that you wrote. The variables are going to go into the RO variable or the data portion of the process. Like down here, the purple and yellow bits, those are going to get read in from a file. Once that stuff is read in, now we're going to set up the heap and the stack. Exec is probably making, in fact it is, exec is making some malloc calls prior to the program actually starting up. And so the heap is already going to be initialized at that point. That first malloc is going to go out into the wilderness block and split that essentially to create some space in the heap. And then we'll sort of start with that initial allocation. But the heap is already there by the time we start up. The next thing that happens is the stack is set up, and really all the stack setup is loading up. Where am I? Runtime stack. I'm going to load a register on the CPU called the stack pointer, and it's going to be loaded with this address right here, that boundary between the system and the user space. So the user space stuff ends at C00000 blah 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 blah, and then this picks up at the next byte. So that's basically the 2/3, 1/3 split, right? So I've got a gig of space up here. I've got 3 gig down here. So the top of that 3 gig is where the stack starts. And really all the initializing the stack means is I'm going to take that memory address, whatever it is right there, add some small random value to it, actually subtract some small random value from it, and then load that address into the stack pointer in the CPU. And now my stack is initialized and I'm ready to roll. So we're going to use the stack for a couple of things, and we'll get back to these registers in a moment. We're going to use the stack for a couple of things. The big thing is that when I make a function call, we're going to call them procedure calls in assembly language, but when I make a function call, that's like it's like leaping out into the wilderness. Like that function lives at some address in memory. It's not contiguous probably with where I make the call, right? So like normally our programs are going to start at the first instruction and then run each instruction in turn in order that they appear until I have to do something like a function call. Then I've got to go find the function. It's somewhere in memory. I don't know where. I've got to look up its location in memory. That's going to be in a symbol table. It's going to be in a symbol table down here. Blah, 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 blah. It's going to be in this portion down here. There's going to be a symbol table with the addresses of all my functions in it. So we look that up, and then the next execution, like the next thing I execute is going to be the first instruction of the function. So I figure out what address the function lives at, and now I'm going to jump and start executing instructions over there. How do I get back to where I was? Like that's a real big leap, right? Like I'm running here, and now all of a sudden I'm running a function over here. There's going to be a return out of that function. I'm going to have a return statement. Where do I return to? Well, I got to keep track of where to return to. It's going to be the next instruction in the original spot. I got to jump back there and start executing again there. Well, that's got to be stored somewhere. So we're gonna use the stack to store things like the return address to go back to the original place in the procedure. If there are parameters that I'm sending into a function, in certain cases, I'm going to use the stack to place those parameters on a stack. So when I do the function call, the first thing I can do is just pop those values off the stack. And now I've got the values that I need for my function. And there's some limits to that. We'll see that toward the end of the lecture. Like those are the biggies. Those are the biggies. Basically, I'm using the stack as scratch storage for things I need to remember, but I don't need to keep permanently. Like I need to remember that return address, but once I've jumped back to it, like I don't need to remember it anymore. Once I've passed those values to a function on the stack, like I don't need those anymore. So it's just really, it's like scratch memory. Let's talk about those registers. So I mentioned this one already, RSP, stack pointer. Let's take a look at the CPU. And by the way, so this is, I guess this is sort of the first lecture where we're starting to really get into like the system side of things. Like to this point, it's been mainly focused on C. We're going to shift our focus now more on the process side and start looking at kernel structures and how the hardware is managed by the operating system, how we access that stuff from our code. So we're going to be more in assembly language, at least for the next several lectures. And I still haven't figured out yet, like, I would love to give you guys an assembly language programming problem set. We took it out of the course a couple of semesters ago. I'd like to add it back in. I'll have to think about how to do that. I mean, it used to be like, you know, back when I was in college, like, it was just assembly language. That's all we did. It's like your intro courses were in assembler. It's not that hard. Like, I think you'll see that assembly language is actually a lot easier than C, much easier. There's just limited things it can do. Oh no, you'll love it, Jaru. You'll love it. All right, anyway, inside the CPU. So there's a whole bunch of registers inside the CPU, and they're varying size. Yeah, Janice. They're varying sizes. We use those registers for all sorts of things. You can think of the registers as being variables, but they're fixed, like they're fixed name variables in fixed locations on the CPU. So we have all these things. Like, we can compare values, we can store flags. Like if I do a computation, I can see, did that addition overflow? Like, it was a really big addition and overflowed 64 bits, or did I subtract something? Was the result of subtraction 0 or not? Like, I have flags like that. If I do an addition, subtraction, something like that, I can results in a register. In fact, they normally do get stored in registers. Like, I can just hold whatever I want. They're just 64-bit variables that I can stick whatever I want in there. And then what happens when a process is running, I alluded to this earlier, like a process runs in the CPU, and by running, I mean it's executing instructions in that program, in the process. It's only a really short period of time. Like, it might be only a millisecond that the program is running, and then something else needs to run. I can't just let a program take the CPU and just completely, you know, hog it, like run for 3 or 4 minutes. It just doesn't work. Ian, I know we always have to check Ian's name to see his current mood, right? Yeah, it's not like our program just runs and runs and runs. It runs for about, you know, a millisecond or so. It's called, the time amount is called the quantum. So it runs for some quantum, and then it gets pulled out of the CPU, and some other program gets to run. That's called a context switch, switching context between processes. Well, all of these registers, like, every process has its own copy of the values in those registers. There's only one set of registers on the CPU, but each process has its own values. So when I do that context switch, I'm pulling one process out and another one's going to run. I've got to save all that stuff. I got to save things like, you know, where was I in the program? What was the program counter? What's the next instruction? All of the register values, they all have to be saved. Tons of other stuff, the stack pointer, the heap pointers, like, all of that has to be saved. And then I do the context switch to the new process. And when the new process starts up, the first thing it has to do is load all of its values into all of the registers in the CPU. So context switching is really, really expensive in terms of time. And it's all housekeeping, right? It's not actual any work being done. So we try to keep the context switcher, that's scheduler code, scheduler.c is where that code lives. A lot of assembly language in there because we want it as tight as possible. So the CPU itself, it's got a bunch of registers. And these registers, they're literally on the CPU. We were talking about this in A1. This thing is just always in the way. Yeah, so that's not a very good picture of it. Oh, there's that one. We're looking for pictures of i7 dies. That's not a bad one. So that's a CPU chip. That's an i7 CPU chip. It's like a quad core. Or is it more than, is that an 8 core? How big is that? I can't find it now. Here we go. i7 Extreme. Let's look at something that's not so extreme. But yeah. Oh, it's the Haswell. That's a new i7. Yeah, so there's a CPU. It's got 8 cores. Looks like 8 cores. So these are CPU cores, these guys. And each of these cores, like each of these CPU cores has, these are probably, I'm just guessing at some of this, these look like registers. So here and here are gonna be my register space. This stuff in the middle is cache memory. So that's cache on the CPU. I've got some power conditioning stuff. I'm gonna guess this actually looks like video processing to me. So that's probably the video chip that's sitting on the CPU. And this is IO, these are IO buffers. So these are the memory and address lines going out to main memory. Actually, those are the buffers over there, sorry. Anyway, yeah, it doesn't look like a picture it fell down correctly. One of my first jobs out of college, so my undergrad was in electrical engineering, specifically in microprocessors, like microprocessors design and controllers and so on. And one of my first jobs was to pop the lid on CPU chips, and these were early ones, like the 4004 from TI. Pop the lid, look at this stuff in a stereo microscope, and draw the circuit, like draw all the transistors and resistors and capacitors and so on. And it was because we didn't trust the company. They told us what it looked like. They gave us the schematics for the CPU, and we needed to verify that manually. So I was the low guy on the totem pole, so I get to look through the microscope and draw the stupid circuit out. It turns out that there were a few differences that we found. Anyway, so this is where the registers live. We're going to say these are the registers, these little blobs in each of the cores. They're literally on the CPU silicon, and they're there because we want them to be as fast as possible. These registers, and again, you can sort of think of them as variables that the kernel is going to use, that the CPU is going to use. They're used constantly. Like we're constantly moving stuff in and out of these registers. If they were slow, everything would just slow down completely. It would be a disaster, to the point where, excuse me, it's an Ivy Bridge. Here's a motherboard. That's the CPU chip here with the yellow sticker on it. And here are memory slots down here. So I would put RAM in there. That's where my main memory would go. It's pretty far away from the CPU, like really far away from the CPU, because you got to remember the signals that are running through this board, like in all the chips and everything, they're limited by the speed of light. And really, the signals going through these chips are some relatively large fraction of the speed of light, like 70, 80% of the speed of light. That's still like, it takes time to get the signal from here to here. Grace Hopper used to carry, Admiral Hopper, she was an admiral in the Navy, US Navy, and was responsible for things like developing COBOL, the language. Grace, Amazing Grace was a pretty big figure in computer science, but she used to carry around a spool of wire. I'll have one handy, but she carried a spool of wire with her, and she would say, "What's this?" And people would say, "Oh, that's a bunch of wire." And she would say, "Nope, that's a nanosecond." Because it would take a nanosecond to get a signal. Electricity from one side of the wire to the other was exactly 1 nanosecond long. So it just takes time to get a signal across these regions of the motherboard. Like if I had to store all those registers out of main memory out here, it would be an eternity to get to that stuff. It would just take a really long time. And so those are stored like here. More cores, like they're stored like right on the CPU, right? Where's our other picture? This guy. They're stored right on the CPU. So there's not a great distance to go. That's the fastest memory I can possibly get. Same with cache. So the CPU's got cache memory. That's all this stuff. Little. And it looks like the Haswell is set up with individual caches for each CPU. Some chips, like I think AMD Opterons, for example, I believe they share cache, which makes it a little more complex. These look like level 1 caches, one for each CPU core. which is cool. But the same thing, right? Like I want cache memory, the CPU level 1 cache, that is to be as close physically as possible to the CPU chip itself, because I can't spend time sending a signal out to the other side of the board to pull stuff out of cache. It's got to be right on the chip itself. And this chip, by the way, like all of this stuff is about the size of your thumbnail. It's a really, really tiny piece of silicon. So that's where they live. That's where all these registers and the condition codes live in basically another register that we treat as individual bits, as flags. The program counter, all of that lives on the CPU. And this one, what's happening is like when our program's running, I can only run instructions that are in the CPU. But for the most part, our program is out in memory somewhere. And so the instruction cycle, like the operation cycle is, oh, I'm going to go fetch something from memory. I'm going to pull it back from memory. I'm going to execute that instruction. I'm going to place the result back in memory and so on, or I'm going to stick it in a register somewhere. Like this is happening at the tick of a clock. The CPU, let's see if we can find the clock. Oh, man, it's been a really long time. I don't see anything that's obviously a clock on this, and they should have a central clock. There's sometimes there's an external clock, but I don't think the Haswell has an external clock. One of these blobs is not like her, and it's going to be the clock for the chip. I know, where's Waldo, right? The clock is ticking really fast. Like when we look at a machine, and like this one, about this Mac, this is an i5, I think. So that's a 2.3 gigahertz quad core. The 2.3 gigahertz part means the speed of the clock. A gigahertz is a billion ticks per second, essentially. So 1 gigahertz, 1 billion ticks every second. This machine's running at 2.3. So every time I snap my finger, half the population of the planet dies. No, it's a 2.3 billion operations. So boom, 2.3 billion clock ticks, 2.3 billion things have happened in the CPU in that amount of time. And of course, there's some smaller subset of that because some things take more than one instruction or more than one clock tick. But that's essentially a machine cycle. That machine cycle, like we can generalize that to be a clock tick. So what's happening as we're running a program is tick, the clock ticks. I go and ask for something from memory. Tick, it's returned to me from memory. Tick, I put that instruction into the CPU to execute. Tick, it executes. Tick, I put the result of that execution in a register somewhere. Tick, I go and get something else from memory and pull it back and so on. Well, as you might guess, like here, this cache, if I had stored stuff here, like this is where my program is going to live, out of main memory on this board. If I had to go out to main memory every time I wanted to execute an instruction, that takes a really, really long time to get all the way out to main memory. I got to go through a memory controller. I've got to go through a virtual memory unit. We'll talk about virtual memory in the next couple of lectures. Like there's a lot of work that happens to fetch a byte from memory. And so the first time I grab an instruction for my running program, I'm going to grab a whole bunch of stuff. Like, oh, I want this instruction at this address. But what I'm really going to pull back is the next 100 instructions. And I'm going to stick them where? Here, in cache. So they're going to go into cache memory because that's really, really fast, right? So I'm going to spend the time to go out to memory to grab some instructions. But while I'm there, I'm going to load up, man. I'm going to pull back as much as I can that's around the instruction I wanted. There's something called locality of reference. I'm going to load up my cache with those because odds are the next instruction I need is the next one that was in memory. Well, I just got it in cache, so I don't have to go to memory to get it. Usually like these boxes, it used to be the cache hits were pretty low, but now in these Intel, especially Haswells and these guys, they're running cache hit rates of like 99%. So 99% of the time when you look for an instruction, it's in cache. You don't have to go all the way out to memory to grab it. It speeds things up quite a bit. So that's what's happening though. It's like, it's this clock tick. The CPU is driven by a clock. Tick, 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 tick. And on every tick, something happens. It feels like everything's happening at once. But the reality is the CPU can essentially execute one instruction on a clock tick, and then it does something else. It's just doing things in order really, really fast. So it seems like it's all happening simultaneously. And especially when you get to multi-cores and so on, it's much more complex, of course. Like that's what's going on the CPU chip. And even memory, like I'm going to use the registers on the CPU chip to manage memory as well. Like what address do I need to go and grab? Well, there's going to be something on the CPU that has that memory address, so I can go and refer to it out in main memory. All right, so that ticking of execute an instruction, execute an instruction, execute an instruction, that clock drives something called a program counter, the IP. R stands for register. So the instruction pointer or the program counter, it keeps track of what the next instruction address is to execute. What's the next thing I'm going to do on the next clock tick? I just said all that, didn't I? So all sorts of things happen on each clock tick. So that RIP is one of our registers. So we've seen two now. We've seen the stack pointer, RSP, and we've seen RIP, which is the instruction pointer, which is the next instruction. Stack pointer, it just has the value of the top of the stack. That's it. Bless you. So let's look at some Intel registers like on the CPU, just so we get a sense of what they are. And by the way, there's two different ways to annotate these things. We're using the AT&T system, which has been in existence since the 70s. So Unix, Mac OS, Linux, all of them use AT&T nomenclature. Windows uses something else, and I honestly have no idea what they look like on a Windows box. You guys who are on M1s, like we're looking specifically at Intel architecture. You are not on Intel architectures anymore. You're on Apple Silicon, and it's a RISC CPU, reduced instruction set CPU. So your stuff is going to look completely different than what we're seeing in lecture. And my M1 guys is you can work in your container and look at stuff in the container because it's emulating an AMD chip, as I recall. You can hit the CSA servers. Those guys are running Linux on Intel chips, so you'll see stuff on those servers. Spin up a Linux box, like it's just going to look really different. Or just like in your head, just map stuff over. We'll have to figure out how we're going to work with assignments with the M1s. But those are just different architectures, they have different instructions. All right, so the registers generally are 64 bits wide, all of them. And then for historical purposes and backwards compatibility and so on, we can subdivide those 64-bit registers into smaller pieces. So they're always the same size. These are baked into hardware. They're not changing. Always 64 bits wide. And the way we refer to them, like the name we use, tells us whether we're using the full 64 bits or some subset of that. Actually, here we go. Here's some. So here, these words in gray, these are kind of historical terms. Like this is like when I started programming, my first language was assembler. So, we would talk about the accumulator. It happened to be the AX register, but we called it the accumulator. We would put counting values in B, data went in C, and so on. So these were historical names that we used for these, and you'll still run into these words. I still use them, of course, because they're baked into my head at this point. So you still see these in references and so on. But like we're not really restricted. In most cases, we're not restricted to what we put into a register. This is just kind of traditionally the way that they were used. The whole thing across here, like this whole piece is 64 bits wide. So RAX, for example, is a 64-bit register. If I want the 32-bit version of that, it's EAX. So depending on how I refer to that register in my assembly code, if I say %EAX, I'm talking about this, the lower 32 bits. If I say %RAX, it's the whole 64-bit width. And somebody asked what the E meant. So originally these were 16-bit registers. Actually, originally they were 8-bit registers when I started. But Intel, the Pentiums came out with 16-bit registers, and it was AX, BX, CX, DX, and so on. Well, when we started getting bigger CPUs, we got into 32-bit CPUs. Those registers were called extended registers. So I had an extended accumulator, an extended counter register, and so on. That's what the E stands for, just extended. So it's an extended accumulator, extended BX, extended CX, and so on. And then when we got 64-bit registers in the more modern architectures, well, they had to call them something else. So it's just R for register now, and then AX, BX, CX, and so on. So that's where the different names came from, at least. There's also 7, 2, 4, 6, 8. Of course, there's 8. There's 8 general purpose registers, R8 through 15. Or if you just need 8 bits, so if you just want 1 byte out of that, you can use R8B, R9B, and so on to get just the lower 8 bits of that register. But these are just like, these variables, like these are typically used just for scratch stuff. Like, oh, I want to save this value, or I'm going to do a calculation, whatever. I'll just use these registers as sort of scratch space. They didn't really have any special purpose in the older architectures, and they still don't really. But I've got a ton of registers, right? Like all of these, like there's 8 here, I got 8 here, 16 registers that I can play with, and then the subsets, of course. That's a lot of registers. Now, I'm not going to really touch all of them. For example, the program counter, RIP, I'm probably not going to touch RIP much. Stack pointer, I probably will mess with stack pointer because I'm going to use that runtime stack to store stuff. So I'll hit the stack pointer. I guess really it's just the program counter I don't mess with too much. Indirectly, we will. I had like 42 questions at this point in A1. It's like, you guys must be the smart group. All right, so let's talk assembly language, right? This is like our first real look at assembly language. So Intel assembly language grew out of like assembly languages for the really early chips, like the 4004, the 8008. Really was the Z80s in 1979, 78, 79. The Z80 chips came out, and they had a more modern assembly language. Prior to that, it was really primitive. Like assembler in 8008 was extremely primitive. When I got into Z80 level chips in 78, 79, those had 60-bit instructions, 16-bit addresses, and so on. So they were a little more robust. And really, they haven't changed much on the Intel side from those early days in the 70s up until now. We've got extra instructions, but all the old instructions are still there. I mean, there's not much you can do in a CPU. So the instruction set is pretty limited to begin with, and even more limited on like an M1. The whole point of an M1 is I've got really a small number of instructions. I just use them a lot over and over and over to do stuff. That's the risk part, the reduced instruction set part. So let's take a quick look at some assembler. So overslicing comments. Nice. Like this is our first look at this is Intel assembly language, x86 assembler. They're really, really simple, guys. I still don't quite know why we took it out of the course. So if I want to move a value from one place to another, I use the move instruction. I use move. And these are always the same order. So it's always the instruction, the source of the thing I'm working with, and then the destination. So where's it coming from? Where's it going to? Source, destination. It's instruction, source, destination. ISD. Means something, I'm sure. So here I'm going to, let's just move a value 4 into a register, the RAX register. Well, move is the instruction. Numbers, like actual values, like literal values, are prefixed with a $sign. So this is a value, that's a number. I can tell because it's got a $sign in front of it, and it's in hex. So I'm gonna move the value 4, that's the source. What's the destination? Register RAX. It's a register because it's prefixed with a %. That just tells me it's a register, and that's the name. So move a 4 into RAX. What if I want to move what's in RAX somewhere else? Move what's in RAX to RDX. Just copy those values. So maybe there's a 5 in there or 4 or something. Now it appears here too. And it's a copy. It's not an actual move. This one's more interesting. Excuse me. This is like dereferencing a pointer. So what would happen here is that RDX is going to have an address sitting in it, some memory address, and then the parentheses, that's sort of value at kind of stuff, or that star dereference operator we use with pointers. So I want to put a value in the memory address that's stored in RDX. So it's an indirection, a first level indirection. So that's it. Just take whatever is in RAX, that's the source. The destination is the location stored in RDX. So if that RDX was storing like, memory location 1, 2, 3, 4, 5, at the end of this instruction, 1, 2, 3, 4, 5 would hold the value that was sitting in our. There's no check as to what is in RDX. No, Jonas. No, there's no check whatsoever. So we're working with raw bits in memory on the CPU. Like if you're doing that, like we just assume you know what you're doing. There's not a lot of checking going on. It's like, oh, you got the key to this? Like you look at, you know what you're doing. Like, okay, whatever, like just go do it. It can be a value, it can be an address. It's just bits. We're just moving bits around. So yeah, it could be anything. And really, Jonas, it's the context that's important. Like, don't forget, like we're writing this code, right? So we know what should be in there, like what we're going to use it for. So it's not like we're just putting a value in and letting the CPU magically guess what we want to do with it. Like we're being very explicit about what's happening at every line. Yeah, theoretically we should, yeah. You can shoot yourself in the foot for sure in an assembler. But frankly, you're not going to break anything, right? It's just bits. So those are move instructions. Easy, right? My first assembly program. Those are just moves. I can use offsets if I want. So these are also moves. Like this one looks similar to the last one we just looked at. So this is moving what's in the address stored in RCX. So previously I've put an address, a memory address in there. This is going to take the value out of it. So I'm dereferencing it essentially. I'm going to take the value and stick it into the accumulator RAX. This one's a little more interesting. It looks the same, but now I'm using an offset. So I still have an address here. I put an address in RBP. This says move the value that I'm going to start at RBP, but then I'm going to go 8 bytes away from that. So 8 bytes up. So if RBP has a 10 in it, this is going to look at like at the address number 10. This is going to move the value that's at address number 18. So it's 8 away from RBP. What's in RBP? That's called an offset. And it's a really, really common thing to do. This is actually just like, you know what this is? This is exactly like dereferencing a pointer into an array. So I've got an array and I want to see the 8th item in the array or the 2nd item, right? Because they're probably 4-bit ints or something. So I start at the array, which is RBP, and then I go 8 bytes up from that and read the value. Just like saying pointer plus 1, pointer plus 2. Now it's pointer plus 8 in this case. Except it's 8 bytes, it's not 8 ints. Easy so far, right? I love assembly language. Can you do it with bits? Yeah, in fact, you are just doing it with bits. Like it's just bits everywhere. We're just talking bits. We're down at the bit level. Oh, instead of bytes, I see what you're saying. No, I don't think so. I think you're probably limited on the offset to byte boundaries. You could construct something that looked like it was crossing a byte boundary, I suppose. Like that 2 bytes next to each other, right? Part of it on the bottom and part on the top and lay them next to each other. I think that would be awkward though. Here's math. Math is easy, despite what Barbie says. Barbie always says math is hard. Math is easy on the CPU, but again, it's source destination, right? So all these are, it's just add, subtract, multiply, divide. There's add, there's subtract, there's multiply, integer multiplication. But notice there's no divide. There's no divide. Division is done by successive subtraction. These guys, SA and SH, those are shifts. So I'm going to shift bits left or right within the context of a byte or a word. We'll actually have like a whole lecture on bitwise operations coming up probably in a week or so. Exclusive OR, an AND, here's an OR. Now notice this is actually an important point. In every single one of these, the destination is overwritten. So it's the source and destination. The destination is always where the result goes in this case. So whatever was in the destination is going to be written over. If I want to save it, if I want to save what's in the destination, I would just do something like this. Actually, I do something like this. Just move whatever is in the destination into another register, like put it over on the side, or maybe push it on the stack. I could do a push. And then when I'm done, I can read it back or pop it off a stack. Edwin asks, is there any significance to all the queues? Somebody else asked that too. Move queue, add queue, sell queue. It's a conspiracy. I can't tell you. No, what happened was, so the original instructions out of like 8008 land were add, sub, sal, sar, XOR, and so on. The queue, revolution against stacks, right? The queue was added just to indicate that we're working with the extended instruction set. So this is the Intel extended instruction set. These actually all work without the queues. So if I just want to say add, that works just fine. Add queue is the correct way to do it in this architecture, but for backwards compatibility, add works as well. I tend to write the queues just because I'm used to writing the queues at this point, but you can do it either way. Actually, well, in here, you should use the queues. In real life, you can do it either way. Here's some single bit stuff or single operand stuff. So increment, decrement, negate, not. And notice this work on the destination. So after I do an increment, destination has destination plus 1. It's fun, huh? This is cool stuff. I think it's cool. How about moving around? Question. What's the difference between neg Q and not Q? Neg just flips the sign bit, and not, I think, flips all the bits. So if I had 1, 1, 1, 1, not would be 0, 0, 0, 0. If I had 1, 1, 1, 1, which is like a minus something, and I did a neg, it'd be 0, 1, 1, 1. So I'm pretty sure neg just works on the sign bit for signed values. That reminds me, we got to think about ones and twos complement math as well. A lot of stuff to talk about in this class. Did you guys do twos complement in CS210 or anywhere? Yeah. All right. You get to learn twos complement math soon. How about moving around? So I said that, like, we're running programs one instruction after another in sequence, unless something happens like a condition or I do a function call or something, which means I'm going to have to move somewhere else. It's like, here's an example. Here I'm going to subtract a couple of values, and then I'm going to check a flag. There's a whole register for flags. See if I can find a picture of it. x86 condition flags. Any pictures? I'm all about the pictures, you know. Not a lot of great pictures. People sub-optimizers, holy moly. Types. Conditions tested. Let's just tells me what conditions I'm testing. 2, 3, 4, 5. Basically, there's a register, a 32-bit or a 64-bit register, where each bit means something. So, for example, one of the bits means, hey, I've just done a mathematical operation like an add or a subtract. There's a bit that says, was the result of that 0 or not? So it's the Z flag, the 0 flag. And so here I'm using it. I'm saying let's move an 8 into RAX. I'm also going to move an 8 into RBX. So I've got an 8 in 2 registers, and then do a subtraction. So I'm subtracting RBX from RAX and storing the result in RAX. That's the subtraction line. And then at the end of that subtraction, the condition flag for 0 is going to be set or not set. Actually, it's going to be set for this one because it is 0, right? So if it's not 0, I'm going to jump to some address. If it is 0, I'm going to jump to some other address. Like I can use those condition bits to do tests, like logical tests. Those are just like if statements. If this is true, then go do this. I'm testing those condition bits. There's a whole bunch of condition bits. There's an overflow bit. If I'm doing 64-bit math and I add 2 numbers together, for example, I'm probably going to overflow that value because it's going to be larger than 64 bits. The overflow flag will be set to tell me there was an overflow, and I've got to go deal with that. So condition bits are used for conditional statements in assembly language, if statements, essentially. For example, here's some code. So here's this test function up here, test func. And this is the result. And how I got this was I used the compiler to output this. And this is actually a really common thing to do when I just want an object file. I'm not going to do any linking, so I'm not creating an executable file. I just want to create an object. Let's say I'm writing a library. Actually, you guys probably could do this too. Like your list functions, you got all that nice list functiony stuff, add a node, delete a node, and so on. Well, you could just do this sort of thing and just output list.o. Now I've got an object file, and anywhere you want to use that stuff, you don't have to compile it again. It's already compiled and works perfectly, right? Most of you works perfectly. So you compile it, you test it, it works great. Store the object file off somewhere, and then my next problem set, when I want to use my list functions, all I really have to do is include the header file and then link in the object file. I don't even need the source code anymore. I've already compiled the source down to an object. So that's what I'm doing here. I'm saying, give me just see test.o. And the flags I'm using for the command line, -G stores some debugging information, things like line numbers, symbols, and so on to help in debugging. The -C says, you know, I just want the object here. I do not want to do the full link. I just want to output an object file. This is -O, and it's an O level of 0. O is for optimization. What happens in C is that the compiler looks at your code. So it examines your code, the way you wrote it, and then the compiler decides if that's what it's going to produce or not. Many times it rewrites your code. It calls it optimization, but what it's really doing is rewriting your code. It's writing it to be more efficient, typically. For example, if I had let's say I had a big, a loop, just a giant loop. Loops are expensive because I'm going to be jumping around in memory in a loop. When I get to the bottom of the loop, I got to jump back to the first instruction. Like that takes some time to get back there. I got to load the program counter up. I got to, you know, it's going to take a couple of machine cycles to get back to that spot. It'd be much faster if I just could run all of those instructions right after at 100 iterations of the loop. Well, instead of jumping back 100 times, the compiler will unwind that loop for you if you ask it to optimize the code. And it'll say, oh, you know what? It's much faster if I just do 100 copies of that code and just change the value of the counter all the way down. Because that way I'm just running, I start at the top and I just run it all the way top to bottom. I don't have to do any jumping. So optimization will change the mapping between your assembly code and the C code. And for this sort of demonstration, like I want no optimization. So I set O0 because I want this code to match this code as closely as possible. I mean, it's short code. It's probably not going to optimize that very much. Actually, we did this over on this side. Yeah, we did it this way. So I've got test.c. I wonder why the GCC is there. So I get test.c. See what's in there. Yeah, so it's this function, right? And then we just ran the compiler against it. We did this. So that's the same line. Give me debugging symbols and stop after the compile BIP, and that gives me test.o. And then I used a command called objdump. Objdump, obj dup dash d says disassemble, like take the, there's binary in the object. If we cap the binary, it just looks like this. It's just junk. It's just binary code in there. What kind of file is it? So it is a 64-bit relocatable little endian x86-64 instructions with debug info. Stripped means that the strings are still in there. I haven't stripped any strings. Those are going to be labels and so on. So that's what the file is. I can use objdump to examine the file. So if I do objdump, demo-big D gives me the disassembly. And what is it, test time? Let's run it through less, just as a pager. So we get this. Actually, test func is right at the top. This is all the stuff that's in the object file, and you'll recognize a lot of this. Well, most of it is debug stuff. So these are all my debug symbols. I thought this would debug oranges. It's like, oh, why do they have oranges in there? I don't know. The line stuff is like, this is information about line numbers in the source code. Debug strings, which you don't care about. Common stuff. Where are my frames? That's the first frame, a stack frame. Somewhere here is the symbol table as well. Should be debug symbols. Must be in the debug info piece. But right at the top, there's our test function, right? And we can actually just see that with a little d. Little d just says disassemble any executable portion of this file, and we just get that. Let's compare that to the C. Are you guys cool, or did I like kill everyone? We all doing okay? It got really quiet when I started popping assembly language up. But let's look at this. Dead. Jiro's dead. Not quite, right? But let's take a look. So what are we doing? Here's our function, right? What's the first thing it does? It puts a 1 in this variable location called 1. Well, the first thing we do down here, it looks like we're going to save off RBP. So that push RBP, push means push it onto that user stack that's at the top of memory. So I'm going to save RBP for some reason. And then I'm going to, this is source and destination. I'm going to take the stack pointer, RSP is the stack pointer. I'm going to move it into RBP. That's actually a really common thing that we'll do at the start of every like subroutine call, little procedure call. We're going to save off the stack pointer essentially. And now I'm going to, so that's all housekeeping. This line number 4, this move, so I'm going to move the value. It's a value because there's a $sign, right? Move the value 1. What's the destination? There's an address sitting in RBP. What's the address? It's the stack pointer address. So I've got the stack pointer address here, and I'm going to put a 1 4 bytes down from that. So I'm essentially moving the stack pointer down 4 bytes. That grows the stack by 4 bytes. So remember, the stack goes down, right? This is 18. Here's the stack up here, and it grows from the top of memory down. So by subtracting 4 bytes, I'm actually going 4 bytes toward the bottom of memory. Sweet, so I'm gonna put a 1 there. So I've got a 1 in that location. And now what am I doing? I'm doing a compare. This is if 1 is greater than 0. What am I comparing? I'm comparing the thing that was that 1, right? That's where I stored the 1 right there. I'm comparing it with a 0. Well, the result's going to go into that spot in memory. Now, that comparison is going to result in the 0 flag being set or not set. If they're the same value, the 0 flag gets set. It essentially does a subtract. If they're the same value, 0 flag is set. And so the very next line of code, so that was if 1 is greater than 0, right? So I do the compare here with 0, and that's going to be a 1 in that memory address. And now I do the test. If it is less than or equal, so basically if they were less than or equal to each other, I mean not greater than, I'm going to jump. J is for jumps. Anytime you see a J as the first letter, I'm going to jump somewhere. I'm going to jump to address like 18. What's at address 18? A no-op. So this is the case where it is less than or equal, means it wasn't greater than. I'm going to skip all of this, right? I'm not going to execute the body of the if statement. And so it says, oh, just jump down here. What's down here? NOP. NOP is no operation. That's a dummy instruction. It doesn't do anything. It doesn't change the value of anything, just takes up a machine cycle. Because I don't want to do anything if it's not greater than 1. If it is greater than 1, then this comparison is going to fail. And what does it do next? It moves a 2 into that location in memory that we've been using, because that memory and location we've been using is essentially this variable 1. And so if that comparison is true, I'm going to move a 2 into 1, the variable 1. And that's what happens right there. And then I do the no-op, and then I pop. I'm going to pop that RBP value and then do a return. This guy is a void function, so it's not returning any values. It's essentially just, it saves the value of RBP because that's the caller, saves it, and then at the end it pops it back so that that value is still in, it's back in the register as just as if we started the call. And then return is just a return from this subroutine. See how it maps? Like you can read this stuff up here and then see down here what the mapping is. It's cool, right? And by the way, like these things over here, what time is it? Sweet. These numbers over here, these are the actual instructions that are generated. So push RBP is instruction number 55 hex. That's it. Like that's how it works. Here I'm doing like this move. The move, you can see that the move is probably these 3 instructions. It's probably, actually might be this even. Like maybe it's C7 is the instruction. 45 indicates, I can't read this. I can't read it in binary. But this maps onto these instructions, these numbers. Because at the end of the day, the way the machine works, remember I talked about the clock? Hang on this question. Jonas says, hasn't noticed skip JLE if 1 is indeed bigger than 0? It's just a compare. So here's the comparison. Is 1 bigger than 0? That's the compare. So I've already moved 1 into RBP, or at least that stack location. So I've moved something there. I'm comparing it with 0. As a result of that compare, the 0 bit's going to be set or not. And I can see, is it less than or equal? If it was, do the jump. If not, do the instruction. And that maps onto this if 1 greater than 0. So Jonas, I think the bottom line in your question is the instruction itself, the compare, sets a condition bit. The JLE is checking that condition bit.
Okay, can you hear me? Yeah, okay. So I get the condition bit. So then it puts something somewhere. But how does JLE know where to look for that condition bit?
Oh, it's built into the instruction. So JLE means check that bit. And then if it's set, do one thing. If it's not set, don't do that.
But where is that bit?
That's that single bit, that Z flag. Those are the condition registers I mentioned a few minutes ago. So there's a whole bunch of conditions like 0, overflow. There's a whole bunch of flags basically.
Okay, just knows where to look because it's
Yeah,
always in the same place. Okay, gotcha. So if I
it's
would put, sorry, yeah.
no, go ahead.
So if there is, if I have two compare statements, then the first one will basically be deleted, and then the second one will be checked. So if I have the the compare statement and another compare statement, then the first one is basically lost.
Yeah,
Okay.
because it's going to overwrite that bit.
Okay, gotcha. Thank you.
You got it. It's literally baked into the silicon. That's a really good lead into this. So these numbers, by the way, these numbers, these are just binary values, right? These are zeros and ones. They're binary values stored in memory, and then eventually they get to the CPU. Like when the clock ticks, that number 48 in binary, 64 bits wide, is presented at the input of a bunch of logic gates, like actual physical logic gates. At the next tick, we look at the output of those logic gates to see what the result is. And then, the next tick, maybe we use that value somewhere else. So, like, for example, if I'm doing addition, let me just do this real quick. Oh. Sorry, I'm gonna grab my iPad. It's like addition. Addition is just a couple of gates, right? If I wanted to add a couple of bits together, keynote, play. So let's talk about addition. So let's say I'm doing single bit addition, like 0 plus 0 sort of thing. So if I've got two values, let's make them X and Y. So X, Y. I want to know what the sum of those two are. And there's going to be a carry bit generated, right? So I add 1 and 1 together, I get 2. I've only got 1 bit, so it's going to be a carry bit. You probably have seen this in 111 or 112. Yeah, so let's just write them out, right? So here's the values: 0, 0, 0, 1, 0, 1, 0, 1, 1. Those are my 4 possible values of X and Y. If I add them together, well, 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 2. And I write 2 as a 1, 0. So I've got a 0 here and a carry bit. And these are no carries here. Like, just look at them. What's the sum look like? That looks like an exclusive OR, right? An exclusive OR is it's a 1 on the output if one or the other inputs are 1s, but not both. So that's an exclusive OR. Let's just write an exclusive OR. That's a horrible exclusive OR. That's just horrible at drawing these stupid things. Bip, bip, F me. X, Y. Coming out of that's the sum. What's the carry look like? Carry looks like blah, blah, blah. It looks like an and, right? An and is true if both inputs are true, but that's it. That's an and. So here's my and X and Y. That's the carry. That's a single bit add with a carry. And if I need to add 2 bits together, I just put 2 of those down and carry the carry through to the next stage. I can build that up to add 64-bit values. I just have 64 of these little guys, carrying the carry through in each spot, so that if I wanted to add two 64-bit numbers, I'd have 64 inputs on one side of this. They would all be just these, and shoot, like an and, you can make an and a logic circuit out of 2 transistors. An XOR I think is, XOR is probably 3 transistors. I think I can do it in 3. So it's not that many transistors. Like a 64, I've got 5 times that. It's 300 something transistors. I got 4 or 2 billion transistors to work with. So my addition circuit is just going to be a big bunch of these. One clock tick, I put a 64-bit value on one side, on each side. Basically, I run 128 bits, right? 64 plus 64. The next clock tick, I just look at the output, and I get the value for the sum and the carry. That's what's happening in the CPU when we write an instruction like A plus B. It's running it through gates like this on a clock tick and reading the binary values coming out the other side. And that's what's really happening inside the CPU. We should build a CPU. That'd be fun. I had to do that as part of my undergrad electrical engineering course. We had a vacuum deposition system, and we didn't do CPUs. We designed, I think we were doing op amps, operational amplifiers. We had to design the op amp and then basically lay down the circuit on silicon in our vacuum deposition system. Those were the days. That was a real degree. I only did engineering because computer science hadn't been invented yet. No, that's just what I said. Just what I said. Let's talk about the stack, like the stack itself. And we don't have that many. Yeah, just a couple more to do here. Actually, I'm running out of time anyway. So the stack comes into play, and I'm talking about this stack inside the process. That comes into play in a couple of situations. So the most common is when we're calling a function. When I call a function, I might need to pass stuff to the function, and I might need to read stuff back out. I for sure need to save the instruction pointer because I need to know what the next instruction is coming out of the function call. So for example, if I've got this, here's test func, and I'm going to call test func2. So I got test func1 and test func2. So I'm going to first set a 1 value here, and then go and run this function here. So here's this is these first two lines are housekeeping, right? But now I'm going to, why am I subtracting that? Subtracting a 10 from RSP. Oh, what's happening here is, so this line is actually just making space for the function call. So if I subtract 10 from the stack pointer, that just gives me 10 bytes of stack space that I can work with. And now I can take that, so the stack pointer is stored in RBP. I've just moved it up by 10 bytes, and now I can start moving stuff around. So I can move a 1 into 4 bytes from the start of that stack. So the first 4 bytes are going to have a 1 in them. That's int 1 equals 1. And now I'm going to do a move, but I'm going to move this. I'm just storing this value over here in the accumulator. And then I'm going to store that value in EDI. EDI is used in function calls to pass values. So that's going to be the first value I'm passing. It's put into a register. And here's the call. So that's this bit. This is this call right here. First, I move the 1 into the right spot into EDI. And now I do the call. And I'm calling, it's like location 19 somewhere. Test func1 plus 19. That actually doesn't look like the right spot. Well, let's see what the next function does. Just func2. Same thing. It's going to do some housekeeping. And then see, it grabs that value in EDI. That's the value I passed in. So it knows, and again, it's baked into silicon. It knows to look for the first parameter in EDI. It goes and grabs it and sticks it into that stack location, does an addition. Oh, it's a plus plus. So it adds 1 to it. And then moves it back into the accumulator. On a return, look, I'm returning an integer here, right? On a return, the return value is going to be in the accumulator register. That's why we can only return one thing in C, because we only have one register that we're storing the return value in. So I do the addition, place the result in the accumulator. Then I'm going to clean up and do a return. That return comes back here, right there. And now I'm going to go to the accumulator, which has the result of the call, and move it into the next 4 bytes. So the first 4 bytes I used for the value itself. Now I'm going to move that value into the next 4 bytes. Remember, I set up 10 bytes of stack space here. So 8 bytes of it, 8 bytes up rather, is going to have the value that was in the accumulator. And then we're just going to do a return. And the return, I'm not returning anything here, and I'm done. So the registers essentially are used, I got a minute, right? For small functions. Actually, it's funny, the timing worked exactly the same as A1. For small functions with, well, small parameter lists, up to 6, the first 6 values I pass into a function are going to be stored in registers, EDI, and so on down. If I have 7 of them, 6 of them are going to go in registers, and I got to create stack space for the next one. So I try to avoid using the stack because the registers are faster. That's basically it. I'm going to load up the registers with the values passed. When I jump into the subroutine, when I do the call, it knows to start looking at those registers to grab the input values. It should know how many there are. And then when I exit that function, it puts the result into the accumulator so that when I do the return Q, RETQ, that return says, hey, I'm done, and your value's in the accumulator. And then I can move on from there. So some things are being stored elsewhere, like RIP, that instruction pointer, that's got to go somewhere. There's a couple of other structures the kernel uses, they got to be stored. They're all going to go into something called a stack frame. And stack frames are where we'll start on Tuesday next week because we are out of time today. So that's it. That's a first look at some of this stuff. And we're just going to keep digging deeper and deeper and deeper until, until we just can't take it anymore. And hopefully it'll coincide with the end of the semester. All right, guys, that's it. Go home, enjoy Thursday. I'll be offline Thursday, but online the rest of the time. And I will see you all next week. Peace out. I stunned everybody. Bye, Jones. We're finally getting into the fun stuff.